So we will now look at linear and quadratic discriminant analysis. Last time we looked at statistical decision theory, and statistical decision theory says that the best classifier, assuming a symmetric loss function and so on, is the one that has the largest posterior probability at a given point in feature space. So if we have a symmetric loss function, then this is the Bayes classifier. Now, Bayes' theorem told us that the posterior probability of label y given point x in feature space is given by the class density, probability of x given y, times the prior probability of observing a given label divided by the probability of observing any point at that location in feature space, or the PDF at that point if we have a continuous distribution. So we know that. The problem is we don't have these quantities, and we need to somehow estimate them from training data. And now the approximation that is used in linear and quadratic discriminant analysis is to make the following assumption. Namely, to say that the probability of x given y is a normal distribution. And making this assumption, we can now ask for the decision surface to construct our classifier, and the decision surface, that's the set of points for which we have that, again, assuming symmetric loss function, the probability of class 2 is the same as probability of class 1. And we can now insert the right-hand side of Bayes' theorem, and if we do that on both sides, we see that we can already cancel the denominator because it's the same on both sides. So we are left with, we can equivalently write, this is probability of x given 2 times p of 2 and we will now use the PDF of the Gaussian distribution. So this was some normalizing constant x minus mu 2. So the mean of class number 2, then covariance matrix of class number 2, and the whole thing is multiplied with the probability of class 2. And then we have something similar on the other side. Okay, now we can multiply out, take logarithms, rearrange a little bit. So I'm taking the natural logarithm, and I then find that now we have the term which is quadratic in x. terms which are linear in X. And scalar terms here. And something similar on the right-hand side. And we can now group and bring everything on the left-hand side. So first I will have the ln of P2 times C2 divided by the prior probability of class 1 times the normalizing constant of the Gaussian for the first class. Then I can group the terms which are quadratic in X by writing the following. So this is the covariance matrix for the second class and the covariance matrix for the first class. Something like that. You tell me the potential mistakes. Okay, so if we step back a little, what we see is that we have a term that is essentially X transpose and then some matrix A X plus this is a vector times X plus a scalar number. And that's a small x here. So this is the set of points at which the posterior probability of one class is as big as the posterior probability of the other class. This is the decision surface, and the decision surface is, depending on the precise parameters, is given by quadrics. And quadrics, well, this is a set of bilinear functions. This comprises ellipses as the most prominent members and hyperbolas. Parabolas. And parallel lines too, I think. So, that still has these unknown parameters, namely the means and the covariance matrices of these two classes. And we can now estimate them from the data, provided we have more points than dimensions. I can show you this thing in terms of pictures. So if you see on the upper left a data set that we saw before last time, and now on the bottom, if you concentrate there first, the blue points here have been approximated with the Gaussian distribution. So the mean of the blue points was estimated, and the sample covariance matrix of the blue points was estimated, and taken together, it means a blue set can be approximated using this Gaussian, which is here indicated by its blue contour lines. Similarly, the red class was fitted by a second Gaussian, which is shown here. And now the set of points that's specified by this equation that we've just seen, the set of points is given by this green ellipsis. Okay, so the green ellipsis is now our classifier. This is our best approximation in terms of quadratic discriminant analysis of this particular data set. And if you remember what the true classifier looked like, so this is the same data set, and I created this data set artificially from the densities that you see here. So the green line here gives the base classifier, the best possible classifier. And on this other slide, you have just seen our approximation to it, namely here the approximation by quadratic discriminant analysis, and I think it's not a bad approximation. Well, this looks about right. And indeed, for this kind of data set, you know, we have quite a few points in 2 dimensions. I think QDA would be a reasonable choice. So because we get out such a quadratic form, and because our decision surfaces will be quadrics, this is called quadratic discriminant analysis, or QDA for short. Okay. Now we can look at the number of parameters this requires. At first sight, you might think that we need all these parameters in the covariance matrix, which grows quadratically with the number of dimensions. Yes, the required number of parameters does grow quadratically, but it's not quite as bad. So because if you look at this formula, it looks like we need the full covariance matrix for the first class and the full covariance matrix for the second class. But if instead you look at this somewhat more abstract form here, you see that we need just to estimate the parameters in one matrix, which is symmetric. So this matrix A is symmetric. So this will be, if we work in dimension p, this will be p times p minus 1 over 2 parameters. This will be another p parameters for this vector plus additional parameter here. Okay, this is quadratic discriminant analysis, and if in addition we can make an even more simplifying assumption, namely in a linear discriminant analysis, we will further assume that the covariance matrices for the two classes are the same. And if they are, well, then this quadratic term here cancels out, and this one becomes a little bit simpler. Overall, this makes life easier. I could write the formula. So the decision surface becomes the ln of the ratio of these prior probabilities. The normalizing coefficients then also are the same, so they cancel out. The quadratic term cancels out, so we are left with plus mu2 minus mu1 transpose. And now I'm just using a single precision or a single covariance matrix without specifying what class it belongs to, because we just have one, times x. minus Can I make the simplification, or is that wrong? Nah, I'm afraid I have to write it out as above. So with mu2 and then a separate expression for the mu1s. Or again, writing it in a more abstract fashion, I now have some other parameter, B transpose X, plus I can collect these two in some coefficient which will not be the same as that one up there. So this is the Euler representation of a straight line or plane. So our decision surface now is a plane, and or it's linear, and hence the term linear discriminant analysis. You also see something interesting here, namely if we now start to twiddle with the priors, so changing the prior probability of one class versus the other, it does not change the angle of my plane at all. It just changes its distance from the origin. So this becomes a parallel shift of the decision surface. So if we change the prior probabilities, we obtain a shift of the decision surface. Let's look at LDA for this very same data set. This is what you see in the top row. So here the same covariance structure has been used for both classes. But even so, there is a difference here between the contour lines are at a different distance. Can you explain why? So this is the LDA fit to this data set. And why do the contour lines look different? Covariance function is the same, yeah. So because the covariance structure is the same, I would have expected the contour lines to look the same. So we have different means. This is the one mean, this is the other mean. We have the same covariance structure. So what's the last ingredient that we have? So if we go back to this formula, this PDF and that PDF by the linear discriminant analysis assumptions, they're identical up to the mean, which can be different. But the priors, of course, still need to be estimated from the data. So in this particular case, we have more red points than we have blue points. And this is why we estimated a lower prior for the blue class. So this results in a down weighting of the blue Gaussian, and this is why the contour lines look a little bit different here. So this is in fact why, you know, it has fewer contour lines, meaning we have lower density. So what is plotted here, just to make it very clear, my escape button has given up on me. So just to make it very clear, what I'm plotting here is the probability for the x given class 1, but multiplied with the prior probability of class 1. So this is, and excuse this auto-capitalizing, which I didn't want. Okay, so it's the fact that I also estimated this prior, which has somehow depressed the whole blue distribution. And also as a consequence, my decision boundary now has been shifted in this direction. Because, you know, remember that changing the prior probabilities results in a shift of the decision surface. If I had used the same prior, then the decision surface would have been right between the two means. And by the way, well, this is of course a bad model. Okay, so if I want to build a classifier for this problem, and I now get the green line as a result, so the green line would tell me everything to the right of the green line should be the blue class, and everything to the left should be the red class. This is a very poor fit for this data set. So that happens when you misspecify your model class. And we will look at this in this semester. You know, in 2 dimensions, you can just look at it and say, okay, it looks wrong. But in higher dimensions, well, you need to somehow estimate if your model was a good fit or not. And we will look at techniques like cross-validation to answer that question. You're very quiet. Please ask.
Maybe again, why is the decision boundary shifted to the right if the prior for red samples is larger than for blue?
Okay. I will just show a sketch in 1 dimension. So in 1 dimension, let's say we think that class 1 is centered here and class 2 is centered there. And if I now just put a Gaussian on each of these, my decision surface will be nicely in the middle between these two. If now I start increasing the weight of one class at the cost of the other, you know, I will get a much larger Gaussian, and I have renormalized such that you know, overall I get a probability of 1, and my decision surface now has been shifted from here to there. Okay, and the same thing in 2 dimensions or in any dimension. More questions, please.
Again, to the contour lines. What is the prior probability change from the one fit to the other? I mean, we estimate the prior probability out of the given points in any case, so it should be the same.
You know, it's really the deficiencies also of my plot. I think my keyboard doesn't like chalk, and the escape button no longer works. which is really bad. So the top row here was for LDA, and the bottom row was for QDA. Okay, so it's the same data set, which I should have perhaps have plotted in the middle between these two rows. Yeah?
You asked why the contour lines, the distance increase from the QDA to the LDA model. And I don't know, and your answer was that the prior probability is now another, but we calculate.
Okay. Yeah. No, I was asking about the difference in the contour lines between these two distributions, because they have the same covariance structures. I would have expected, naively, the same contour lines between the blue and the red one here, and they're different due to the different prior. You are right. The prior, the estimated prior would be the same here and there, but even so, we see many more contour lines here. But the reason is that this distribution is narrower, so it has the same mass as that one, but it's much narrower, so it has higher PDF, and this is why there are more contour lines. Any more questions?
I'm looking there at this forum with quadrants, and I think I don't know if is wrong what I think, but there in the back QMG, second one,
Yeah.
has attached companion matrix, because it's really nice there in second one, second line. Yeah.
It has attached what mappings?
Companion.
Companion. I don't know these. Companion metrics.
Yeah. It's a matrix with one on principal diagonal, and also one on the last line, and on first, second position on the first line has one under P, and third position.
No, I don't think so. I don't think so, because so here A, is just the difference between these precision matrices, and the way they will look like, it just depends on how your data is distributed, and you don't know that in advance. So yeah, please check, but I don't know these companion matrices. Okay. So the decision surface for LDA is just a plane, and we could make this formula even simpler by further assuming that the covariance matrix is isotropic. So the covariance matrix is just a multiple of the identity matrix. So if in the LDA case, if in addition we would assume that the covariance matrix is just a multiple times the identity matrix, then the decision surface will just be a plane that lies right between the means. This is also called the closest mean classifier. If the prior probabilities for the classes are the same, then it comes to lie in the middle. Okay, so we estimate a mean for one class, we estimate a mean for the other class, we assume the prior probabilities are the same, and then the decision boundary we would get is just the line that lies orthogonal to the shortest connection between these two. So that's an even stronger simplification. And in this sense, well, for LDA in general, this decision surface need not be orthogonal. We can get skewed surfaces here, and you can view that as a sharing of your feature space. Okay, change in the priors, we also stated that leads to a shift of the decision surfaces. And this whole approach only works if we have non-singular. So both LDA and QDA as presented here, they only work if those matrices that we estimate if they are non-singular. If they are singular, well, we cannot invert them, and then we need to resort to regularization methods. So how can regularization work? Because these are important methods, many alternatives have been proposed. And one due to Friedman is called regularized discriminant analysis. So again, let me ask you, QDA and LDA. We saw in this example that QDA fits much more nicely. So why would you do LDA at all? Why is this a reasonable method at all?
Maybe it's faster, and maybe there are examples, there are data there it performs better than on this data, and you know it, and then.
So one argument is it's faster. You also said that there are data sets where it might work better, but LDA is a special case of QDA.
Yeah, I mean better than in the example shown there.
Yes.
Seems to be ridiculous, but
Yeah.
Isn't the data that there the LDA performs better than the QDA?
Yes, there is data where LDA performs better. The question is why?
Could you maybe change the feature space in a way that you increase the number of dimensions? For some, if you have a good transformation that doesn't fit, then you should be able to separate with a plane, which is easier than separating with a quadratic in lower dimensions.
Yes, you can do that. But why is it sometimes better to have a plane than a quadric? Number of parameters, yes. Because you see here we have something of the order of p square parameters to estimate. Here we have only of the order of p parameters. And when we have too few points and too many dimensions, you're likely to overfit. It's just like in, say, linear regression. If you offer too many so-called explanatory variables, you can always obtain a fit, but this is not going to be predictive. You have just overfitted. Yeah? So LDA is of interest because it is less susceptible to overfitting. QDA is interesting because it's more flexible. And now this regularized discriminant analysis, it offers you a compromise between the two. So first of all, you can mix. It has two steps and two associated parameters. The first step allows you to mix the individual covariance matrices with a pooled covariance matrix. I'm going to put this in a quotation mark. So mix the class-specific covariance matrices with a pooled covariance matrix. This pooled covariance matrix, I'm just going to call it sigma hat without any subscript. And that can be summed over all, I'm assuming that we have C classes. In this previous example, we just had 2 classes. And then we weight it by the number of samples that we have in a specific class and multiply with this class-specific covariance matrix. So now this is a summation sign, and this is a sigma. Okay, let's say this is a sigma, and this is a sigma, and this is a summation sign. So this is the pooled covariance matrix, and we can now obtain this mixture that I mentioned by saying that this class-specific covariance matrix as a function of a parameter alpha can be obtained as a mixture of the original class-specific covariance matrix plus a modicum of the pooled covariance matrix. Now we have a mixture between LDA and QDA. So for alpha equals 1, we get QDA, and for alpha equals 0, we get LDA. But we have incurred this additional parameter alpha. And we're going to study means, I think 2 or 3 weeks from now, of how to fix this parameter alpha. And now secondly, you can also mix in some degree of isotropy. So bias a class covariance matrix This is also a way of eliminating parameters, because I had already mentioned that we can set a covariance matrix to just a multiple times the identity matrix. Then we have just a single parameter to estimate rather than order of p squared parameters. Okay, and this will give us a second parameter, so that overall we have a sigma I hat function of 2 parameters now, alpha and beta. And now we have a normalizing factor involving the trace. And the dimensionality. And we mix in a little bit of identity matrix of dimensionality p. So now we have a second parameter that we need to fix, alpha and beta. And with these 2 parameters, we can now find any compromise between LDA and QDA, and between having isotropic covariance matrices or full covariance matrices. Okay, so overall, we have now found a method that is very different from k-nearest neighbors, because, those blackboards are very close. So k-nearest neighbor estimates or can be seen as estimating the posterior directly. So in k-nearest neighbors, we ask how many samples of a given class are in a local environment, and this can be viewed as estimating the posterior. And on the other hand, we have now used a very stiff parametric model by making this strong assumption that we can put a normal distribution here for this class density. There is nothing justifying this assumption. Okay, this is just something people do. You know, if they don't have better alternatives. So because we don't know what the true densities are, we can use any estimator for the class density in feature space. We could use much more flexible methods like kernel density estimation that are even more susceptible to overfitting. And it seems that the normal distribution is not such a bad compromise, especially if you have relatively few points in relatively many dimensions. So in particular, if you have few observations in high dimensions, then I would rather do LDA than k-nearest neighbors. So k-nearest neighbor is a very flexible method, again using those words from last time that I still haven't properly explained. K-nearest neighbor has low bias and high variance, and LDA on the other hand, it's a stiff method, so it can have bias, but it has relatively low variance. So we have seen these methods that somehow span, or these are somehow extreme methods. They span the space of possibilities, and then throughout the semester we will look at more alternatives like you know, the neural networks and support vector machines and all that. But before that, we're going to look at Gaussian graphical models today, because we don't finish early each week. But before we do that, I would like to know if you have any more questions. Not now. Okay. Find me in the break if you have any.